welcome to the conclusion of the college algebra videos on synthetic division and the remainder theorem. So in this video, I'm going to focus on the remainder theorem. Be sure you've already watched the video that shows how to do synthetic division. I'll be doing a little bit of synthetic division in this video, but you should already have that skill kind of under your belt before you try this. So what is the remainder theorem? The remainder theorem is kind of a conclusion or a set of conclusions that we can draw after dividing a polynomial by quantity x minus k. Synthetic division is typically how we do that kind of division. So here are some of the conclusions we can draw. First of all, the remainder from synthetic division is the function value f of k. That is, the polynomial that we start with is some kind of a function. When we do synthetic division, we actually find the value that would result if we put k as the input of that polynomial function. For instance, a, b, c, d, and e here are representing the coefficients of the function f. If I do synthetic division with the number k, I get a series of outcomes leading up to a remainder. Whatever that number is, that is exactly the outcome I would get if I put k as a value into the function represented by that polynomial. So f of k is equal to that number. Now, a side result of the remainder theorem is this. It's called the factor theorem. If you do synthetic division and the remainder here comes out 0, well, there are actually two things that we know. First of all, we know that plugging k into the polynomial function would give you a value of 0. But you also know that x minus k, that quantity x minus k, is one of the factors of that big polynomial you were dividing. So x minus k is a factor of f of x. Let's take a look at a couple of examples to illustrate these points. So we're going to ask ourselves, is k a 0 of this function? If not, then what is the function value at k? So as you can see, my function is f of x equals negative x to the fourth plus 3x squared minus 4x minus 5. And I'm checking the k value of negative 3. Now remember, that would be the same as dividing by the quantity x plus 3. So let's see how we do this synthetic division. I'll set up my guidelines here. Negative 3 is the value of k. This polynomial has a coefficient of negative 1 for x to the fourth. It is missing an x to the third term, so I need a 0 placeholder for x to the third. Positive 3 for x squared, negative 4 for x, and negative 5 is my constant. I'm going to do the synthetic division here, where I add and multiply. Negative 1 plus nothing is negative 1. Multiplying, we get positive 3. Add, 0 plus 3 is 3. Multiply, negative 3 times 3 is negative 9. 3 plus negative 9 is negative 6. Multiply, negative 3 times negative 6, that's 18. Negative 4 and 18 is positive 14. Negative 3 times 14 is negative 42. And here's where everything is determined. Our remainder is negative 5 plus negative 42. That is negative 47. So first answer to the first question, is k a 0 of the function? No, my remainder did not come out 0. If not, then what is f of k? Well, the function at negative 3 is the same as that remainder. It's negative 47. Now, if you don't believe me, we can check that on a calculator. Let's pull up a calculator here, and Here's that calculation. I put -3 into this function. Negative of -3 to the fourth plus 3 times -3 squared minus 4 times -3 minus 5. And that does indeed equal -47. So the remainder matches the function value. That's the key idea here. Let's take a look at another example. Same two questions. Is the k value they gave us a zero of the function? If not, then what is f of k? Oh, and look at the value of k they gave me here. It's not even a whole number, integer, anything. It's an imaginary or complex number. Well, turns out we can still do synthetic division with complex numbers. The number I'm dividing by is 1 plus 2i. The coefficients of my polynomial are 1, -2, 4, 2, and -5. I've tried to space these out a little because I have a feeling I'm going to need that space. Let's do our add multiply process. Add 1 plus nothing, and I get 1. Multiply the complex number 1 plus 2i times 1, and I get 1 plus 2i. Now I need to add these up. Well, the real parts, -2 and 1, add up to -1, and the imaginary parts add up to positive 2i. So we add that real number to that imaginary number. This is what we get. Oh, now I've got to multiply 1 plus 2i times -1 plus 2i. All right, let me quickly do the FOIL here. Some of you may be able to do this in your head, but just to make it very explicit, we're going to FOIL these out. First times first, -1. Outsides, positive 2i. Insides, -2i. Last times last, positive 4i squared. And remember our concept of that imaginary number, I is the square root of -1, so I squared is -1. So that's 4 times -1. That last term is a -4. These middle terms cancel, and in front of that I have a -1. -1 minus 4 is -5. So that multiplication took a bit. Let's continue our add multiply process. 4 plus -5 is -1. This multiplication should be pretty easy. The complex number times -1 is -1 minus 2i. Be sure and distribute that -1. These add up to complex number 1 minus 2i. And now we've got to do the multiplying again. Okay, let's FOIL these again. 1 plus 2i times 1 minus 2i. First times first is going to be 1. Outsides and insides will cancel out again, a minus 2i and a plus 2i. Last times last is minus 4i squared. And when I squared turns into -1, that's the same as 1 plus 4, or a value of 5. So multiplying, I got 5. The remainder, -5 plus 5, equals 0. So that answers the question, is k a zero of the function? Yes. Also meaning that if I put f of 1 plus 2i, so use that complex number as the input for my function, I will get an answer of 0. Thank you for watching this video, and if you're in my college algebra class, you should now attempt to do the assignment MyMathLab 3-2. Again, thanks for watching this video. We'll see you next time.